Laura won the local math Olympiad and was awarded a magical ruler. With it, she can draw, as usual, lines in the plane, and she can also measure segments and replicate them anywhere in the plane. But she can also divide a segment into as many equal parts as she wishes. For instance, she can divide any segment into 17 equal parts. Laura drew a parallelogram ABCD and decided to try out her magical ruler.
Okay, can I stop just for a second? Sure. So everyone so far understands what things she has? She has this magical ruler, and who can remind me what this magical ruler can do?
Draws lines.
Draws lines, okay, that's good.
And she also won the local math Olympiad.
Oh yeah, okay. But that's
It's a true story.
It's a true story. There was a Laura who won the BMO 8 this year, but that problem was written before
She won. Well, that must have motivated her.
And by the way, I just heard the news. Laura is in 6th grade. She qualified for MOP and went there for the Math Olympiad summer program in Nebraska. And they have some tests there, so she's on the U.S. team to go to the Girls' Olympiad in China.
She's on the first team with the, there's 3 high school students and 1 6th grader from the Bay Area.
So, yeah. So at any rate, yeah, the problem was quite suitable. She solved it and she left 2 hours early. The Olympiad. All right. So we have a magical ruler. We can draw lines. We can also replicate segments. But the magical thing is,
You can divide it into any amount.
any amount. So with the regular ruler, can you do this? Can I just divide, you know, a segment exactly into exactly like 113 equal parts? No. No? No, I don't think with the regular ruler you can do this. But she has a magical ruler to do this. Okay, so then what happened?
Okay. So she drew a parallelogram ABCD.
All right, everyone draw a parallelogram. Okay, and then?
And decided to try out her magical ruler. With it, she found the midpoint M of side CD.
Can she do this? Everyone?
Sure, she has
Yeah.
our magical ruler.
Magical ruler, okay. All right, so that's M.
And she extended side CB beyond B to point N so that segments CB and BN were equal in length.
Can she do that? She can draw the line and she can replicate the segment. Okay.
Unfortunately, her mischievous little brother came along and erased everything on Laura's picture except for points A, M, and N.
Okay, there we are erasing. Okay.
Using Laura's magical ruler, help her reconstruct the original parallelogram, ABCD. Write down the steps she needs to follow and prove why this will lead to reconstructing the original parallelogram.
Okay. So while you were thinking just a little bit about absorbing the problem, I can tell you some funny stories from the grading. And I don't know all of the funny stories. I wasn't grading this particular problem. But I was told that there were 2 Russians grading it, and they had a lot of fun laughing together. A lot of the students, one student mentioned that since, you know, it's the brother who erased it, they should just make him come and redo it. Another one, many mentioned that you can't possibly erase everything. They have to be some traces left for you to follow. And then there were some more mathematical solutions too. The nice thing is that this problem renders big variety of solutions. I knew one from 5th grade. I can tell you this problem came from a very old book, Bulgarian book, this one, and I used it when I was in school preparing for the Math Olympiads. It's published in
85.
Yeah, although written in Bulgarian, the numbers are the same, 85. And it's just geometry and algebra, very simple. But my favorite. I have not found anything that can match it. And that problem came from there, but it was changed a bit. So shall I tell you how I changed it before we attempt to solve it? Maybe that will give you a little bit of a clue. The problem was more or less the same. There was no, mischievous brother and so on. But there was no magical ruler either. They just said, these 3 points are remaining, reconstruct the original parallelogram. So what could the Bulgarian textbook have meant? With what tools? Compass and a straight edge. That's what they meant. So a compass and a straight edge. So now I cannot use the markings at all, just the straight edge. And that's the classical set of tools for constructing problems. So if nothing is given, that's what we are assuming. So this is what the original problem was. But then we decided that in America, kids may not be familiar what things they can do with these 2 tools. And therefore, we gave the magical ruler. We threw it to them. Does anyone have a magical ruler at home? Yes? No? No? Brandy, keep quiet. Anyone has a magical ruler? Just admit, do you have? No, you keep quiet. Anyone? No one is admitting. All of you have a magical ruler. Because these 2 together are a magical ruler. That's the point of the whole problem, that students do not know this. That you can subdivide every segment into as many equal parts as you wish if you have just a compass and a straight edge, although several steps have to be followed to build up to doing this. And so to avoid this technicality, we gave them the magical ruler. So we will solve first the problem with the magical ruler, and then we will try to see, do we really need a magical ruler for that? Okay? So how about you work in pairs? The problem is hard if you have not done such problems. Just talk to someone next to you.
Nope.
And there are just a gazillion number of solutions to this problem. So don't be afraid to be creative. Oh, I love this. I love this. Can you do this?
I started by drawing down.
Okay, you can certainly do that. Yeah.
Really great pages.
Nice idea. So, you have drawn it a little bit different.
We can do it. We can look at this triangle.
Yeah, people
I
have a different
have
way
to
of
right now.
imagining
I
it.
just haven't had time because I've been.
But I don't, and so that triangle is this triangle.
And Josh, if you have seen this problem, which you
I have seen this problem, yeah.
and if you would like to try the hardest problem,
Yeah. I thought I'd try the hardest problem. Maybe the second hardest
the
problem.
second
I'm
hardest.
American. I know the geometry.
Okay, all right. So try problem 3A. Should not be that hard. 3B is intermediate, and I'm not giving you the hardest.
Where's the really hard one?
The really hard one is the last one, 5B.
Furthermore.
So if you guys are bored, you can try problem 5B.
This is a good problem to start with.
Oh, you remember that problem?
Yeah, well, who's grading it?
Elena and so they were just laughing in Russian the whole time.
Yeah, I'm sure it was hard to grade because there was so many.
So many differences.
Yeah.
Well, no, the interesting thing is on this problem in the back,
Yeah.
they were all opposite, but it's a
That was
Diagonal of this.
I didn't say worse.
My thoughts are,
Just-
difficult. Can we do this? Can we just do,
The way
that
it was.
DNA? But we don't have to D or D.
The rest were very easy.
Can we draw
And then
perpendicular line?
problem, so he can illustrate it. Then we made
Well, why do you assume that?
Right, so you just have a new rule.
I want to actually draw a slightly more accurate, better picture. Because I want to get some sense. I want to get a sense of.
I wish I did geometry.
Some other kind of some kind of line like that we can draw to get the one
Okay,
the other
because you're not given a template.
I was testing to see if they were the same.
Oh.
Maybe sort of big.
No, I think they can be forming triangles. As long as they're not on the same line.
Yeah, that's just a fixed zero.
This is all just in 1, 2, 3, 100,
Bob, can you teach him on it?
It's really fun.
Okay, that's good. I like connecting these points. Do you think something important may lie on this?
So you have a coincidence too? Yeah.
You kind of see there is one very special point on this point.
Yeah, we
Yeah,
can
could you
translate.
possibly find that point?
Or, I think one of the dangers.
What is your feeling about it? Your picture is not up to scale, by the way, but it is almost.
Yeah.
It's almost to get the right amount of information.
And what we're doing first is
I'm going to change my
robotic translation.
Aha.
Oh,
Okay, now put it this way. A lot of people flip it. Okay, so you guys found out that this point is but it is also what?
Each of us would sort of
Okay,
take
so
turns
we
being
know
What's the
that.
midpoint?
translation.
Okay, because
Segment
right.
CD.
So this is called the mid-segment
Right.
triangle, basically.
It's a
Okay.
tiny little
So you
bit.
can find this point.
This is
Oh,
a
that's
style.
good. So you can now point on this line, so you can
This-
probably construct this
Oh, I
line.
see. It's
We already know
Oh, I see. Because
this
you have
line.
2 parts.
It would be nice to find point B, right?
That,
So let me just, this will link to
half
one.
that, that
Can you
quarter.
find some other things?
That's 3/4.
You just told me that. Okay,
That's two.
excellent insight. This is two.
Half of that.
You okay? So how much is
And then if
this?
you can go 4.
What else is for? Okay, so that's
Ah,
Got it in
I'm there. I found it.
So now which points do you have?
So now that I've got B,
Can we make, oh, I think it's, let's think about some other lines, so let's think about that.
I think I have B, I have M. So now how do I go? Okay, well then I can construct
Yeah, that's a very
a
good line.
parallel line through that point.
Yeah.
Okay.
If you draw it, there might be
Then I-
something special on it.
Okay, but I have no. That would give us this tip.
Okay.
Some calculation.
Okay. I've got M.
Yeah, you know, I like this. You can stop here. So how did you find this point?
Well,
Oh,
I
I'm
think
gonna
it'll
put
have
that
to be
one.
whatever the half
I think I got it.
of this thing, sort of longer
I
is.
think I have
Or
that.
whatever, I don't know, I'm not.
Did you think you had it?
I have a solution.
Okay.
You don't know that you have it?
Well, I think so. I just have to think it through. Yeah.
Do you see some nice triangles here?
Yeah, that's what
What can you
I was,
say about those triangles?
there's some.
Similar, and how similar?
No, I have it.
Meaning what's
I have
the
it.
ratio?
I have it definitely.
I gotta show this side.
Have you got it?
I guess it's.
It's in there.
Because, yeah, this is one side and that side.
Well, you actually don't know about the height yet, but you know this. Because it was given to you. So you already have that those are 1 to 2, so everything else must be 1 to 2. So then if this is your Z. And can you find this point? Remember that you don't want these 2 points. Is there a way to find this point? What's your name?
Correct.
So back to back, there is a 0.
Okay.
Let's put T for tab. And Okay. So is there a way to find DC? You don't have any of those ones.
Sure, yeah.
So you have only A.
Well, I can extend this, so then we got this.
So we would just say
We had one,
Yeah.
right, so we just make it the same distance out there.
Yeah.
These
So
are
you're gonna
parallel.
find this, and now you can do your calculation.
And then we drop there.
This is
You think I was gonna solve that?
2Z.
Then we can find it by drawing here.
Where do you have trying that?
Right.
Look at
Yeah.
anybody?
So what was the order? So we found this one was the one.
Okay. Crazy. So, alright, so now what do you have on the picture? We have midpoints.
Yeah, and then you, and this is where you need the magic. So then you cut this into thirds. And took one of the to go out that way. So this is two.
How would you find the
Geometric reconstructions.
That's right.
There's extras there.
Well, we don't know what that is.
Yeah, thank you. Okay, so any ideas? Yeah, you guys have an idea?
Yeah.
Okay.
You
Connect.
so what you do is you try and construct it from the point of view of this guy. So you're gonna you draw M to N.
So can you do that on the board?
Sure.
What is it in?
David.
David is going to solve the problem.
Oh, but you're oriented different from me. So let's see. You go M to N, and you find the midpoint of that. And I look at mine because mine's a different orientation, and it might help me figure out how to get from there to there. And so between A and N,
So everyone understands he can do this so far, right?
Yeah.
He can connect the points, can find the midpoint, okay?
and this midpoint isn't actually a point in your original drawing, but it's on the line from A to B, because those two triangles were, because the triangle M and C.
You know what, I think we should just redraw the original
Redraw the
diagram,
original, yeah.
so we can have a point of reference for it.
Yeah, that's a good idea.
So let me just A, B, C, D, what was this here?
N,
And
M there.
and this is what
So
we
we've
did.
drawn that. So then this,
Can you label that point here?
yeah, so we'll call it, I don't know, F or something.
Okay.
Okay, and so this line here, okay, so this here, I'm just going to orient myself again because this is not my orientation, but this triangle here, we know that. We know those are the same. And so therefore, these are the same.
Okay. Can someone fill in a little gap here?
Because they oh, sorry, yeah.
Yeah, you said it.
Yeah,
You said
I
it.
was not trying to be the person, but yeah, because they're similar triangles, yeah.
They're similar because AB and DC are parallel.
No, just because they're triangles and because the lengths of sides are proportional. So if this is double that, then this has to be double
And
that.
your
But that's
angles.
because of the parallel lines.
Oh, you mean because these are parallel? Yes,
Right,
sorry.
Okay, so can someone actually say which
Well, that's why
triangles
you
we
know
are
they're
talking
similar.
about? Yeah.
Yeah.
Can you just say what triangles you're talking about? You never
Yeah,
named them.
NFB and NMC.
Okay, so this triangle here and this one here, right? So he's saying they are similar because they have parallel sides here.
Or angles.
And therefore the angles here would be, let's have another chalk or another color. So for example, these angles here would be equal, these would be equal, right? Because of the parallel lines. And that would be enough for the similar triangles. Okay. And then if I understand what David was saying is because now the proportion here is 1 to 2, everything will follow that proportion. So this would also be 1 to 2, and therefore you actually have F to be the midpoint. Okay, all right, so that's good.
Very good. So now also, we don't know where D and C are, but we do know wherever they are, that equals that, because that was constructed as a midpoint, right? And we also know that this is half of that. And because this is a parallelogram, DC equals AB.
So can you give me your favorite number?
Oh, you mean what I'm going to make it? Let's make it 12.
So what
So
is 12?
DC is length 12, let's say.
Okay, excellent. So if DC is 12, then...
That means at CM is 6.
Can we write this?
Yeah, so this would be 12, 6, and that would be 3.
Okay.
And the reason it's 3 is, again, because this is a 2-to-1 similar triangle. So we get this nice thing where this is a quarter the length of the entire edge there. Whether it's 12 and 3 or whatever and whatever. And that quarter, since we've got the magic ruler, we can divide this, so we don't actually have B, but we have A, right? And we have F. So now we can divide AF into 3 equal parts.
Oh, cool.
And that makes it, so each of those is length 3.
So how much is AF total?
9.
9. Everyone sees that? Can we write 9 on here? Okay, excellent.
And so each of these is length 3, and we can extend that line segment one more, 3, and then we found B.
So can we do this on the raw diagram there?
Yeah. So there's F. So what we've done here is we've divided this into 3 equal parts and extended that to there, and so we've located B.
Okay. Now can everyone complete the construction from here? It would still require something to do. What would be the first step? Just tell David what he's supposed to do.
Extend NB to get C.
So you draw MB, and you know that that length, well, what did I call it here? Yeah, it was the single mark. So actually, yeah. So that was the single mark length. So if I extend that same length in the same direction, I have the same length, that locates C. Next.
Oh, we have a teacher at the board, don't look at me. Just answer his questions.
So you have the same distance on the other side to get D.
From where to where?
From C to M,
Yeah.
that same distance.
So C to M I had called 3, which is actually 6. Okay, that's interesting. So if I extend that the same length
To the left.
to the left,
Parallel to AB.
then what? Let's
That would be point D.
Okay.
and we're done.
Voila! Thank you. That was great. That was precisely my solution. And I didn't give them any hints. Now the kids came up with an amazing number of solutions, different. They were just going off here. For example, they would connect any, would find a point here, and it's just, you can make lots and lots of different things. I know of another solution where you can use the diagonals here and see where you can intersect them again with proportions. So for homework, try to create at least 2 more solutions to that problem, because kids can really surprise you on the spot and you have to be able to figure out, is their solution really working or not? Okay, so do we need the magical ruler for this? How many people know how to make a magical ruler out of a straight edge and a compass? Okay, so some, yeah, okay, good. So those people think about problem 5D. With the others, let us very quickly go through this basic geometric construction. So what we have is just a straight edge and a compass, and we want to recreate a magical ruler. Okay? So the first thing I want us to do is just be modest and be able to find the midpoint of a segment. And can we do this with a straight edge and a compass? Let us review it, because not everyone may remember how to do this. And I can tell you that when we started learning geometry, when math split into officially algebra and geometry in 5th grade in Bulgaria, that was the very first thing we did. We started with Euclidean axioms, or rather a version of them. What is, the geometry based on, what you assume as your rules. And the first task was really to reconstruct the magical ruler, although no one was telling us about magical rulers. So this is, we're going back to 5th grade geometry in Bulgaria, which I think should be taught in 5th grade here. Everywhere. In America, the kids are gonna love it. Okay, so we have a segment. Okay. How would we construct the midpoint of it? There are several different ways, but one is kind of classic. Anyone knows? Okay, but do I have a perpendicular bisector?
Well, you take your compass.
Ah, okay. Can you show us
On the board?
Okay. Here we made this very. Let's see, does it draw? It's kind of hard. Oh yeah, it draws. That's good.
Okay.
There you go.
Giant compass. I need to make sure, this is what I have to tell my students, that I have my setting greater than half, just by estimate.
You can make it even equal to AB, just to be sure, and that will do it. But anything, yeah.
Okay, I'll do that.
But I'm gonna now come and
It's a
help
little
you.
loose, yeah.
Yeah. There.
Okay. All right, so I'm going to set my compass at one endpoint. I'm going to just start with B since I'm here, and make an arc above my segment and an arc below my segment. I hope that's working. Is it working? Without changing my radius of my compass, I'm going to set my new endpoint at the other, set my compass at the other endpoint A, and make an arc again above and below, and all I really want to do is find the point where these two arcs intersect, because I know that this point is the same distance.
Can we label
from
the
the
points
endpoints.
that you found?
Let's label them. Originally C and D. And then let's see if it actually worked on the board. I have.
It may not be long enough.
Let's try this.
It's okay. We
all
trust
you
you.
have the idea.
Actually, these are not used for boards, for whiteboard. These are for
So-
chalkboard.
so
Shouldn't
don't
draw.
draw on it.
Yeah,
Okay.
actually, I don't use it. This is just abstract
All right.
ruler.
So
You're not seeing it really.
Abstractly, I draw.
Okay.
I missed.
Excellent.
Sorry.
And then
And
the
then
midpoint.
midpoint would be at these points.
Okay, thank you. Can someone very quickly give me the reason why is this point M the midpoint? Yeah.
So ACB is an isosceles triangle.
Yes.
So those two sides are equal, and the two angles on the far outside corners.
Like this?
Yep.
Okay.
And then let's see. So
We don't yet know that.
Right.
Right.
So if we split the top,
We need to use D somehow. Can we repeat what you just said for D?
yes. So the ADB is an isosceles triangle. So AD is congruent to DB.
Exactly, yeah. And the construction, the way she made it was actually with equal radius on both sides, although this is not necessary. You can change the radius at the bottom. Okay, and so we have,
That angle is congruent to that
but
angle.
officially, are they the same?
Yeah.
Actually, they are, because the way she did it is not only these two triangles are isosceles, but they are
Congruent. Oh, equal.
they're equilateral, because she
So she did it to
That's
there.
right.
did the radius. Again, two isosceles triangles would do the same thing. But actually, these are not the triangles that make it work. There are other triangles here that you should consider. They're not the
CN.
DAC.
CN is congruent to.
And
The left and the right are the two triangles that make it work.
That's the ones that are congruent.
By
So do you
side
see
by
why?
side.
So the
Side by
even
side.
yeah, the top two are equal, and I even made them different from the bottom, it doesn't matter. The bottom two are equal, and is there a third one equal? The middle one is the same. So you literally have two congruent triangles like that. Okay, so what?
Therefore, the altitudes I don't know.
Well, then the angles are the same.
Their altitudes.
Those angles are the same.
The
I
angles
like
are the
that.
same.
This is what you are missing in your original attempt. You needed some angle here.
And so then you've got ASA.
And so now on top,
You've got ASA or whatever you want.
SAS.
Yeah.
and this one. Does this do it?
Yeah.
So now you have two congruent triangles here. So what?
So therefore, the corresponding parts of congruent triangles.
Okay.
Yeah.
Perhaps those that we were interested in, they're equal. And not only that,
They're perpendicular.
you constructed what you were saying in the beginning, the perpendicular bisector.
Yeah.
Okay.
You can't use the middle one, can you?
Can you use the which one?
You can't use the middle side, can you?
Because it's congruent to itself.
Once these two are congruent, and we proved it without the bottom.
She's talking
So
about the
first
two
you prove
smaller.
that the big triangles are congruent, which makes those top angles equal of congruent. Okay. And then now, in the top portion of the picture, right, this is what you have. You know already that these angles are the same. You, by construction, those sides were equal.
Yeah.
And this middle part is literally the
By
same
identity.
side. So you have side, angle, side. No?
No, because you have side for the whole side all the way down. You don't have it for...
No. Here you also have this side.
It's
She's
just
looking at
identical
the-
to itself. Any side is identical to itself.
So what you have here in the top part, so let me label it, A, B, C. Okay, and then you have this point M. Okay? So what do we know now? We know that AC is equal to BC. That was by construction, right? We just showed that the two angles are congruent because of the larger triangles. And this middle side is just itself. That will make what you wanted to say, that the bottom ones are equal and moreover perpendicular. Okay, so from now on we can do perpendicular bisector. I want to replicate as a next step this tool. What is this tool? A T. Yeah, what is a T for? Good for? Right angles, but there are two different things you can do with it. Two different ways of creating right angles. So let's see. The first one is if I give you a line, AB, well, just a line, and a point on it, X, what can you do?
Construct a perpendicular.
Correct. So the word, I think in English is called erect a perpendicular,
Right.
although it could be going down, right?
Yeah.
So you can erect a perpendicular using that T tool. Okay, can we do this with our straight edge and compass now? How?
Make that the middle of a segment.
So the idea is, do what mathematicians always do, right? Being lazy. They want to do less work. So reduce to the previous problem. Because we already accidentally had a right angle here, so can't we just replicate the situation? So this X must be what? If you, must be the midpoint of something.
So draw a circle around it.
Yeah, so you're gonna do, you don't need a, you know, you can go like this. Yeah, okay. So you will have your A here, and this is not going very well. Let's try another one. You're gonna have your A and your B at the same distance. And then we replicate the same construction, correct? As if we don't know the midpoint, but we already know it. It's X, correct? So you're gonna do your thing and create a perpendicular bisector. And where will that perpendicular bisector accidentally pass through? Through X, because it's already given to be the midpoint. And by passing through X, it will make our right angle. All right, but that's one thing. What else can you do with such a tool?
Point is not on the line.
Correct, yeah. So here we are erecting a perpendicular, now we will be dropping a perpendicular to a line. Can we do this?
Yep.
Okay, so let's see. Here will be sufficient. Here is a line, a point off the line. All right, what shall we do? Let's be lazy. Replicate again, yeah, the previous situation. I here draw a circle around it.
With radius.
Large enough.
Yeah.
Okay.
Or make it bigger.
Bigger you need. Has to be bigger.
Really? No.
It's. I guess it could be the same size, but that would be very lucky.
Which size? Oh yeah, it's. I mean, you
You'd have to
can
be very
lock out
lucky.
and make it tangent, and
Yeah,
then
it's not a
you're fine.
construction,
You have your
exactly.
point. But just make sure that the radius is more than what the distance
Yeah,
is.
exactly.
And I think then we are back to this same situation. You can then continue down like this and so on. Actually, what mathematicians would do is they would abstractly draw it. They're actually not going to draw it. They're going to say, well, there is already the algorithm of doing it. So once you have located points A and B, you can just wave your hands and say we are done, right? What do I mean by that? By the previous problem, we know how to construct the perpendicular bisector of segment AB, right? And that perpendicular bisector has got to pass through X. But you have to prove this a little bit, but I think you have some triangles there. So you're basically done. All right, so we can now do whatever we'd like. We would usually do with a T, we can now do it with a compass and a straight edge. So this is, from now on, a standard tool in our BACT, magical BACT. We can use it. I don't have to go through this construction over and over again. I can say I'm dropping or erecting perpendiculars. That is legal from now on. All right, what's the next thing that you see here that you might want to use that we haven't yet done? Yeah.
Dividing into as many pieces as
Oh yes, that would be the crown of this whole discussion. One more step.
Constructing a parallel or a line.
Parallel, that's right, yes. So if I'm given a line, can we, in a point off the line, can we construct a line parallel to the bottom? Let me draw this, that's the next step. In fact, there are many ways of doing it, but there is one kind of standard one following what we've been discussing. Okay, so here is a line, and here is a point off the line, and we'll go back 2,000 years in history to who? To Euclid, right? So there was this very famous fifth postulate, right, that Euclid inserted into his axiomatic theory, and then it caused lots of trouble for people for 2,000 years to decide if that was an axiom or if you can actually prove it, if it was a theorem. And we are facing it. So anyone knows? You said it, but you're not saying it. So if you have a line and a point off the line,
You can construct exactly one line to the point.
exactly, so there exists exactly one parallel line parallel to the original through that point. And so there are actually two statements that you are saying here in one. There exists at least one, and there is no two. And it looks like this should be provable. I mean, it kind of seems obvious, right? And so a lot of people try to, every self-respecting mathematician, right, try to prove this statement from the previous axioms. And there were even published papers that were false. Very famous mathematicians did this. And it was only, when was it, in the 18th century, mid-18th century? There were 3 people. It's amazing, there was no email those days, right?
Yeah.
And so for 2,000 years, you know, the humanity has been trying to decide, is this an axiom? That is it unprovable from the other axioms, or is this a theorem? Is it provable? And so, for example, how would you prove that it is provable? Well, you start from the other axioms, you build something, and you end up with this. Well, all those attempts were false. But how do you show that it's impossible to prove it? You know, the fact that I can't prove it doesn't mean that it's impossible. I mean, that's usually the assumption of people on the street. You know? If they can't do it, then it's impossible. But here in this room, we're a bit more demanding. Right? And so how do you prove, let me phrase the question this way. Is it possible to prove that something is impossible? How do you prove such things? Is it possible to prove that something is impossible? There is one very famous method, and all of you know it.
Proof by contradiction.
Exactly, proof by contradiction. Or you construct a counterexample. In other words, a geometry in which all of the other axioms work, but this one fails. So what is that geometry called? Anyone? Oh, well, they're different names. I think
Non-Euclidean.
Non-Euclidean, yes, thank you. So back to the I think 18th century? 19th? No, Gauss, Bolyai, and Lobachevsky.
Right, so early 19th.
Early 19th? What is early 19th? 18 something.
Early
Okay.
1800s. Yeah.
Okay, so you guys, for homework, figure out exactly which century that was. But it's amazing, within, I don't know, 10 years or something of each other, those three mathematicians, and as you realize, they have different origins, right? German, Bolyai was Hungarian, and Lobachevsky were Russian.
Yeah, I think Lobachevsky and Bolyai came up with it in somewhere around 1840s, but Gauss had come up with it long ago and buried it in this.
Well, there are also stories that actually Gauss heard it through Bolyai, and it just, you know, the blood, battles in mathematics history. This is one of them. And there are also stories that Bolyai really went crazy trying to do it, and when he did it, he wasn't recognized. So, I mean, there is a lot of interesting stories you can read about this. But the truth eventually triumphed, and there was a model which they constructed, and I'm not going to go into the fine details. They're different models, but they actually turn out to be all isomorphic, all really the same. A model of geometry, hyperbolic geometry, where all of the other rules work except for this one fails. And how does it fail? Infinitely many. It's amazing, yeah. They're just infinitely many parallel lines. Do you want me to go through very quickly to show you how this works? Because I can demonstrate it on the board.
Yes.
I'm not going to explain how the other rules work, because actually that's the hard part to prove there. This one is the easy to show that it works. Okay. And students love this. They just completely baffled. They're like, this can't be true. And then you show them that they are thinking that I have to go into some sort of, 4 or 5 dimensions or whatever, some complicated stuff. And say, no, you can actually see it on the board. With some minor details missing, technical details, but we will not worry about them. So the board, the whole world, is just this circle. Okay? My points, I have to tell you what are my points and my lines. Okay, my points are all just the ordinary points inside this circle. Not even points on the circle, and not points outside. Only points inside are points from now on. Lines are chords on this circle. So this is a line. And these 2 points don't exist. They're just for us, for our convenience. They're not our points. So, the lines are just chords on the circle. And then you have to talk about the notions of when 2 segments are congruent and when 2 angles are congruent. And again, I'm not going to go into this. And there are some things that have to be verified in this geometry. But everything can be done very well. I think officially this is called the Beltrami, am I spelling this correctly, Klein model or something? There are different ways of actually defining it. But for us, I just wanted to demonstrate this point. Okay, you have a line, which is a chord, and you have a point off the chord. What shall we call it? C for Colleen. That English. C for clean. Okay. And I'm going to call these two abstract non-existing points A prime and B prime. So they're not points. You don't see them. Okay. Now, how many parallel lines to this one are there in our world? Well, there is this one, oops, right? This chord, which is truly parallel the way we know it. But are there any others?
Anything that doesn't intersect it? Is that
Yeah.
what you mean by parallel in this model?
Yeah, but that's exactly what it means, parallel
Yeah,
on the
so you have
board
to
too.
make that clear that that's what it means, though.
But
Because it isn't obvious, you know, someone is thinking parallel as a geometric definition in the Euclidean plane. they
what is
might-
the definition in Euclidean plane? It's the same.
the intuitive understanding of it, and then you might want to just clarify that
Right.
parallel
So
doesn't mean. it
when
looks
you are
parallel.
talking about Euclidean geometry, you define parallel as lines that don't intersect.
Yes.
No matter how they look,
I agree.
they don't intersect. In Euclidean geometry, it's the same as saying it's like a railroad. You know, everywhere if you drop a perpendicular, it's going to be the same distance apart.
Yeah.
But you don't have to have this in your definition. It's
Yeah.
the same as saying they're actually not intersecting.
Yeah.
Okay, and so you can of course see that they are how many of those? Infinitely many. There's one real special. Look at this. Do you see that one? It's parallel to that. It's not intersecting it. So it's called, I think, the ideal whatever
This is the
one.
Klein model.
Yeah.
So no Beltrami in front?
Well, it's the Klein model of the hyperbolic plane.
Yeah, that's what they said, but sometimes they associate it also with Beltrami. But, you know, these are just finer details. So, with all of this story aside, just to shake your beliefs in, you know, in geometry, and I can tell you they did not introduce this to us in 5th grade. No, they didn't dare yet. But here, I have dared introduce it to 5th, 6th, and 7th graders, and they love it. So, I mean, there's some pros and cons to the different methods of education in Eastern Europe and here. There, things have been a lot more gradual. When you progress through your different courses, sort of the regular track like this, and the math circle track. They're both kind of moving the same way. So at the same grade level, if you pick students from a math circle, you would approximately know what they know. And if you pick students from regular classroom, you would approximately know what they know. And here in America, you know, it's like that. So you are allowed to talk about anything. And you may get the right audience to really, you know, grasp it and enjoy it. Okay, so with that said, we are back to our problem. And we are going to be in Euclidean geometry. And we will assume that there is what? Exactly one. We will assume. We're not going to prove it. We will assume because you can't prove it. You understand? You cannot prove it because they are counterexamples. And this is not Euclidean geometry. All of the other rules for Euclidean geometry work here except for that. I see someone is very puzzled. You've got to be absolutely disturbed about this when you see it for the first time. I was. Okay, so now you will question every geometric problem that comes across. Don't. We're going back to ordinary Euclidean geometry, and we wanted to verify that we can construct, indeed, a parallel line. So if you have a line L and a point off L, okay, how can we construct this parallel line? Which tool can I use? The T. How many times? Twice. 2T. 2T, right? So everyone knows this? You've got, now we can officially, if I can open this, we can drop a perpendicular, and then to this line, which I'm going to call M, right? We can erect the perpendicular at X. And I think we're done. Okay, so that was the preliminary. Now the magic ruler. Do we have a magic ruler? Everyone at home. Can we trisect, seven-sect, whatever it is called?
Yep.
Is it called seven-sect?
I will call it that.
Yeah, once we trisect it, I think we will know how to.
Yeah.
So how many people know how to trisect? Okay. All right, so why don't you work with the people around you and explain to them, and then someone who does not know will come to the board and explain. Who previously did not know but will know.
Okay.
So,
Here's I'm assuming this is the step.
anyone else here?
Basically, so
So-
and you want to.
You don't have to use any more compass because you can. No, you
So take a point
can.
off the
You
plane.
Can you
can.
draw?
Actually, yeah. She might need a compass occasionally, yeah.
And then.
But you can use all of
and
the
then measure
nifty
off
constructions
three
now
equal.
to shortcuts. You can draw parallels, you can draw
just-
perpendiculars,
Can
you
you
can
draw a
write.
segment and know?
All of that you can just say it in words. You don't have to redo
Yeah,
it.
go start with the
So we're looking for a very
Start
short
with
way
any-
of trisecting.
Starting with any segment,
Make it pretty long.
can you draw like
That
a
one.
bigger segment
And
for which you know the
you want to
trisection was?
trisect this
Oh,
up the story?
sure.
Okay, so now measure off
And
by
then these are all
three
similar
lengths on
triangles.
that are
The first one,
any length you like.
No, the original
Yeah,
problem.
but that's not.
You can do that.
that's not-
Yeah, because look at what happened here. This
You're
was.
gonna- I think it's hard.
So that's kind of your ruler.
Okay.
And so then you can use that
Right?
to trisect.
There is a circle
You have the intersect, so I'm making
How would you use this, which you know is a trisector, to trisect kind of in one go?
You had 2 points.
How about the other
Well,
one?
I'm just saying that the original
Then I can't.
Those three are.
Now,
I just don't
I
know
know
how
the
to
angle
this
of
weak
the-
trisect. It's
No,
not
the third
this line from A to B here. I mean, this is one.
I think you can get
I just don't know how we'd
by
apply
one
it.
circle, one parallelogram.
So you want to hook them up.
Oh, so
There
if
is
you
a,
took
yeah.
2 points.
You definitely need to draw it out.
Yeah.
So now you
What else?
connect them.
We need to know where A and M are.
And then it's there's one should be.
That's a good
Backwards from there.
And I gave it at Stanford, Master, but it was sort of.
I didn't like that. That's why I was thinking, even though it's very elegant and bisecting, it would be nice to
The
show
problem
it
is,
this way too.
since they're parallel,
Oh, yeah.
I don't
Generalize.
Since we
get
didn't
that
make
much
the
out
original
of
Process of doing it.
Propose
Main
another
process of
way
constructing
to
a parallel
First
line.
one, they work likewise.
Maybe
There's really no
you
point
want to
doing
construct
that.
bisecting.
So you had one line.
It was a little bit more line.
Oh, should I?
The construction
But
of
there was all
parallel
here.
lines means copy the angle somehow.
What if I made one of these?
So is there like a compass
12 here.
way of copying?
Yeah.
No, you don't have to. I mean, we just did the parallel with 2 perpendiculars.
And then I drew.
I know.
Oh, by the way, there are different ways of doing
Would it
this.
be better
Don't
just
get,
like
stuck with one way. There are many ways of doing it.
And then I came back to that.
I know which is the most
And then you do
efficient,
parallel.
but
I
you
see.
know.
Yeah, I do it a little differently.
It might be simpler to apply.
Not right on top of it.
What you're saying, right? So like,
As I said, I was saying there are different ways.
Yeah, she said they do it a different way from how I did it.
And
Yeah,
there,
so
it's
this
nice
is
to
the
do
one you want to
it
try
with
to
this
just draw it out
number,
kind of in any other.
Right.
but it's not necessary.
I don't know, this is the way I did it was
So you
I
do
just
the
constructed
perspective.
parallel
So you start
line.
with your-
Yeah. So there is
Let's see.
another.
So this is the place where, kind of, one more hit will give it away probably.
And then construct parallel
So
line.
instead of a barrel like that,
Yeah.
Construct-
yeah.
Yeah, so anyway, think about, if
Then you
you,
draw
these are the
that
points
line
you
and
want,
construct parallel lines.
and how can you get
Yeah,
them?
it's anyway we do it.
Yeah.
And this way, yeah, you need a
Which you
parallel
can
line.
do, right?
Yeah.
Yeah.
Okay. That's
But you only need one parallel.
But you need
Whereas this one you have to do all these, construct all these parallels. So I don't know.
So you need,
So you construct your parallel line, so that's.
Because remember, you
so
kind of
that's
needed all that
two
stuff to lead
perpendiculars
up
that
to
you've
the
done.
fact that
You
you can
measure
actually,
off a
I mean,
bunch
all
of
you got
points,
originally is this.
and then you
And
draw
then drawing
these,
these
that's,
two
that's
parallels
just straight edge.
kind of
so
needs
there
all
are two
this
ways
stuff.
to measure things.
Kind of
Yeah.
to get through.
That's,
Yeah.
So
How
it's
many
really all
points?
there.
Yeah.
When you actually
And then how many points you construct.
No, we're not going to do it
Or
over
in
again,
writing
you know,
number
but it has to be
Right,
there
right, yeah.
to draw the
So,
parallels.
for example, for me, drawing a parallel line is just saying one word,
Right,
you know,
yeah.
one step.
Yeah.
So I'm just saying it
Yeah.
depends how you measure it, but
Yeah.
that's not the task here.
Yeah.
The task is that we can.
Yeah.
All right, so who wants to try? A person who did not know before, but now is enlightened and wants to. Yeah, want to do it? Okay, go ahead.
All right. So I'm gonna start with got my segment that I want to cut up. And over here, I just make some other segment. And I'm going to turn that segment into my ruler. So this segment is going to be one part of a segment with 3 parts. And I'm going to do that by extending this line and then making a circle and marking it off. And extending and making a circle and marking it off. And so now I've got 3 segments here. And then I'm going to just draw some random line kind of like that. And I'm going to mark off this thing here. And I probably could have saved myself a step by
just draw that.
Just start out with.
Okay, so can we label the points of the original segment?
So that's going to be A and B. And I'll call this point C, D, and F.
And can you mark which segments are equal now on your picture? Okay, we can do this. Just arbitrarily 3 equal segments there, no problem.
And then I'm going to get tricksy. And I'm going to draw this line. And because we just talked about it for a while, we can make a parallel line here. A line D prime parallel to FB. And then I'm also going to make a line C prime that's parallel to D prime, which is parallel to FB. Now, because these are all parallel lines, and this is one line, this, and this are congruent angles, this, and this are congruent angles, and this angle is the same at the top. So these guys are similar triangles, and since these are all congruent segments, these are all.
All right, excellent. Woohoo! Thank you. And as I said, there are other constructions, and you talked during the break to get, more of them. There is another one here, a prospective one. Okay. Now, this was all to build up to the harder problems. Okay, so shall we? Okay, and there is a really very hard problem, which Dave has been trying to solve in his head while writing an email, and he's halfway through it. We will, though, be a bit more modest and start with, let's see, Tito Andreescu was the old coach of the US team, and when we were choosing the problems for the USMO, he would rate them, easy, medium, hard, and then easy, medium, hard, and then, he had this, oh, that's easy, medium, medium, hard. So he was basically trisecting, the level of difficulties between points. So the problem I will give you is about easy, medium. Okay, it's on your sheet, but I'll just try to, let's see, is it on your sheet? I think so. Reconstruct, if you go to section 4 on page 3, let's see, problem 3A. So, you want to reconstruct a convex quadrilateral ABCD. So this is what Laura draws. And then she draws 3 points, 3 midpoints of, 3 of the sides. So what shall we call them? N, M, and L. So these are midpoints. Okay. Then the brother comes in, right? Erases everything except for these 3 midpoints. There's something more given in the problem, right?
Intersection of the diagonals.
Yeah.
The intersection of the diagonals, okay.
Which problem is this on your list?
3A.
3A.
No, I'm gonna correct my grading scheme difficulty. It's easy medium. It's a little bit harder than what I thought. Okay. So you are given which points after the erase, n, the 3 midpoints, and the intersection of the diagonals. Okay?
Do we know it's convex? Oh, it is, yes.
It is, yeah. And so reconstruct that convex quadrilateral. And let me ask you this question. Does a convex quadrilateral, everyone knows what a convex quadrilateral is? I mean, let me draw for you two that not convex. Something like this. Okay, that's bad. That's outlawed. But there's some other quadrilaterals like that. Do you agree? This is called the self-intersecting. And it's kind of hard to decide, you know, what are the sides, what are the diagonals of this. But the sides are indeed those two things that look like diagonals. So it's as if you took a quadrilateral made out of wire and you twisted it like that. So those are outlawed. We don't want those fine things. We just want the quadrilateral where the internal angles are, what, less than 180, right? And you don't have any self-intersections. And we'll see if that actually matters for the problem. So my question to you is, suppose you talk to your grandmother on the phone. I usually use this example when I talk to my students. So I call my grandmother right in Bulgaria and I ask her to draw a convex quadrilateral. And she draws it. And I ask her to make it as random as possible. You know, no parallelograms, trapezoids or anything, right? And she draws it and I'll still tell her, Grandma, there is something very, very special about your convex random quadrilateral. What is that special thing? And it's partly on the board, it's not yet drawn. But there is something very special about any quadrilateral, even non-convex, even self-intersecting. So no matter what your grandmother draws, there is still something special about that very special figure inside. Aren't you bothered by something given in this problem?
The collinearity of
if you connect
the midpoints and the intersection of the diagonal.
Okay, that will come up a little bit later when we investigate if it is possible to do it or not. What is it?
If you connect the 4 midpoints.
Oh, 4? We're not given 4 midpoints.
Yeah, but you'll find that the 4th midpoint is...
Oh, aren't you missing the 4th midpoint? Isn't it annoying that it's missing? It is. Mm-hmm. Yes. Can we find it? Yeah. How? A bisector? Okay, so I cut off the person who actually knows it. Not let him speak up. So let everyone connect the 4 midpoints. So what shall I call this? M, N, L, P. Okay. So connect the 4 midpoints and just stare at it for half a second and tell me what you see. I heard it. What is it?
I said it right answer. Parallelogram.
It is a parallelogram. It's a very non-regular parallelogram on my board. But it is a parallelogram. Now I'm going to scare you even further. What happens if I do it here on those funky quadrilaterals? Are you going to get the parallelogram too?
Wow, very cool.
How about this one?
Yeah.
Well, I hope I don't land right here on the midpoints because I'm not going to have a line. But I'll pretend I'm just going to make it slightly off.
You put 2 of them on the same side.
What?
You put 2 midpoints on the same side.
Ah, I did. Oh,
No
well,
midpoint on
I
the
hope
other
no one
side.
would notice, but there you go. It's still a parallelogram because it's just the picture is so messy anyway. So. Yeah, so anyone knows how to prove this? So your grandmother, no matter what she's doing with her convex quadrilateral, she's still drawing something special on it. There's always something special in that parallelogram. Anyone knows how to prove it? But did not know before, but now knows. That's a final distinction. You've seen the proof over and over in the previous discussion. It's just there are parts from the previous discussion that apply on this picture. Okay, so are we clear about what we're proving now?
Yeah.
Okay, so that the four midpoints of any quadrilateral form a parallelogram. Yes?
I'm just looking for similar. There's.
Yeah, I'm also looking for similar.
Yeah.
Yeah.
There are similar
I
triangles.
don't, I can't really prove, but could you construct a line between L
Oh, I see how to do
No
it.
LM.
I see how to do it.
Which one? Which?
well, it doesn't really matter, but between L and N? Or
L and N. That would be the diagonal of that parallelogram. However, all of the lines are already on the picture.
Yeah.
All of the lines that you need are on the picture. Okay. So we're looking, I heard the word similar. Similar
Yeah.
what?
Well, you,
Similar triangles. Do you see some similar triangles on this picture?
yeah.
Okay, so David, which ones?
So, well, you've got C, M, and I'm trying to read L, is that?
L.
Yeah.
Okay, so
C,
that
M,
guy.
and L is similar to the bigger one, the C, D, and B.
C, D, this one.
Yeah.
Oh, I'm not sure you can see it, but let me redraw the picture. We again end up in the same situation with the, what's called the mid-segment, right?
Yeah.
So you have a big triangle, D, B, C, and mid-segment here, connecting the midpoints, M and L.
Would it be okay to just pause for a second so you can think about it?
Oh, yeah, sure. So what's given on our picture is that M and L are the midpoints of those sides. This is what's given. And so if you connect NL, this is what's called the mid-segment of a triangle. A segment that connects the two midpoints of two sides. Okay? So are these two triangles really similar? By which rule? You guys know all of this?
Well, the two sides are proportional.
So I hear it from here. Two sides are proportional, proportion
because
1
of the
to 2.
segment,
And
the angle C is
and the angle C is the same.
Yeah. So this top angle is the same for both of those triangles. And then you have proportions 1 to 2. 1 to 2. Correct. We in fact saw this in the first problem, the Bayer-Math Olympiad problem, when you drew this MN and said, oh, well, these two triangles are indeed similar, but the proof there was different. You're using that already you had parallel sides. You're using something different. Okay, so is this good? Is it okay to have these two triangles similar? Okay, so what that they are similar?
You can do it on the other side.
Ah, correct. Yeah, you can do it on the other side. Right? Everyone sees that? So now this guy is similar to the big one. Yeah? So what happens overall?
So the two mid segments have to be parallel because they're both parallel to the mid diagonal.
And actually they are half of its length, isn't that right? Because of the same proportions of the two triangles. So N and P are somewhere down here, the other two. So NM, what was it? ML and NP, each of them is parallel to DB for two different reasons, and half of the length of DB. So what happens if two segments are parallel to each other and equal in length? What do you get? Parallelogram. Of course you can go with the other ones, but it's going to be an overkill. Because there are more similar triangles on this picture. So, back to our problem. Can we find this point P P, the fourth midpoint, the midpoint of the fourth side.
Yes.
Right.
How many of those are there? Well, that's the most interesting part of this problem. So let me just backtrack a little bit. Geometric problems, construction problems, they have several parts, and people usually miss the last one. So something is given, you go about, you give a construction algorithm, step 1, 2, 3, and so on. Then you prove that your construction works. And then the last part is how many solutions are there, and on what does this depend? And that's the part that people miss. And so you're telling me that you can reconstruct point P. Well, how many points P are there?
Well, I guess there's sort of two, because you've got two lengths that you'll be using.
So really what is given, you have to abstract yourself from this picture, okay? You're not given the quadrilateral, okay? So you're just given these points, in fact, I have it here. Okay, M, N, and L, and forget about the point O, it's just not yet relevant for my question. So the question is, where is the fourth point P? So I bet what you are thinking is connect like this, yeah?
Right.
Then draw a parallel, which we can, draw another parallel, and bingo, this is your point P.
Right.
And you're going to be right, except you have missed a couple of solutions. Do you see some other points P on this picture? Can you show me?
I don't know totally how you get it, but you go that way instead.
Aha, that's right. You can go that way.
Right.
And so let me
Get a
draw
really
another picture
long
because we
parallel.
will get all messy here.
So that's why you
No
need
one
the
said that
intersection of
point P has to be somewhere in this area. Point P has to be the fourth point, fourth vertex of a parallelogram.
So that's why we have the intersection, the point of the intersection of the diagonals.
Oh, I see, so it could be everything.
Okay, so you can go this way, right? And there's your second point, P2. So that would be P1, P2. Do you see a third one?
Complete the triangle in either direction.
Ah, that's right. So really,
Oh, look at that.
you construct a triangle, which, by the way, how does it relate the big one to the small one? And you actually flip this mid-triangle 3 ways, and you end up with twice as large size. 4 times the area, but all of the sides are... It's pretty cool, right? So, in effect, you might end up with 3 solutions here, 3 convex quadrilaterals. Okay, well, we're not yet there. We just found, let's say, we located one of those points. So how do we complete now the construction? Point O must be somewhere in it. Okay.
There'll be a break coming
Yes.
in about 5 minutes.
Yeah, so I think we can finish this.
We know the intersection point of the diagonal, so we should
Right.
put those in.
Yeah, okay, so let's say it's point O here, right? Okay, someone gave us point O. So what shall we do?
And then we know the diagonal
Just use the legs.
is parallel to certain segments.
Oh, we already know this. Remember, we were talking about the parallelogram sides being parallel to the diagonals. We already proved this earlier. So you can make the diagonals now, at least the lines, because they're supposed to be parallel to the sides of your parallelogram. You can do that. And now what? Where are the actual vertices?
Equidistant.
Equidistant from... There's some equidistant, but you have to come on the board and show me.
Center point to the edge of the parallelogram to the point, is it not?
Is it here? Is that what you're saying?
From there, there, and there again out.
What's your name?
Sage.
Sage, okay. S, right?
Yeah.
Not C. I'm just
S,
confused
yeah,
about
S for Sage, yeah.
Okay, and so if I understand what you're saying is you want to flip all to the other side like
Is that
that?
not right? Yeah.
It is, right?
Oh.
Because you again have the mid-segment
Yeah,
situation all
mid-segments,
over
yeah.
again.
So it's
If you connect those two, you'll again have that this guy is equal to that.
Right.
As a matter of fact, this is what's happening really all over in this problem. You have a mid-segment, and I'm not going to even label the points, it's all over the place. And you start connecting like that. What do you know about these guys?
They're all.
Yeah. This mid-segment stays mid-segment for every one of those. So all you have to do is take this guy and flip it over. And then you have choices, right? You can, take this and flip over. Or, once you have located one, you can just go about and do it. And I hope I'm gonna get... Am I gonna cheat? Almost, right? Oh no, look at that. Whoa! Are we done?
Well, we have the other two to do.
Yes, so you imagine that there are actually two more P's that you have to do will all work.
Right. That's pretty cool.
So I think we should stop right now and I will leave it to you. The question is, there is something in the initial configuration of the 4 points that may give you 3 solutions or may prevent you from having 3 solutions. How many solutions will you end up? How many convex quadrilaterals will sprout out of this, depending on the configuration, the initial configuration of the 4 points? And what would happen if that configuration is not right? What kind of quadrilaterals are you going to get? Okay, so you can think about that, and we can start having a break.